So let's figure out its magnitude and phase angle. So here first we're going to bring it to a form where you do not have a j in the denominator. So as you guys mentioned last class, we're going to be multiplying and dividing by the conjugate you mentioned, right? So the conjugate of r plus, it's basically complex conjugate. R plus j omega L is r minus j omega L. So you just keep the magnitudes of the real and the imaginary parts the same, and you change the sign on the imaginary part only. So r minus j omega L. So that's j omega r L L r. This becomes a plus because it's a j square. J times j is j square minus 1. And then you have omega square L square, right? Yeah. Divided by r square, negative, negative, positive, omega square L square. Seems okay? So then I'm going to say it is omega square L square divided by r square, omega square L square, the real part, plus j omega r L divided by r square plus omega square L square. Okay, so that's the form like x plus jy or r plus jx. So I don't want to use r and x anymore. So all I'm going to say is this is x plus j and this is y. Okay, so then the magnitude is going to be x squared plus y squared root. And again, angle is going to be tangent inverse y over x. Okay, so here is the magnitude of h j omega. And keep in mind, guys, this is a complex quantity. Those are complex quantities as well, the phasors. Okay, so I'm going to say x squared plus y squared root. So that becomes omega square L square, a square of that. Omega square r square L square divided by same thing in here. So I'm going to take it common. And then a square root. Okay, so I can take, what can I take? Omega square L square. Right? I'm going to take omega square L square common, so it leaves r square. In the second one, since it was a square of the quantity, so it leaves as it is. R square plus omega square L square are square, so one of this will cancel, and one will be left. So what we're left with is omega L divided by square root of r square plus omega square L square. And you can kind of put it as omega L whole square as well. So where I'm writing omega square L square, you can write it as you can write it as omega L whole square as well. Okay, similarly, the phase angle. So I'm going to say the phase angle of H equals to tangent inverse y over x. So where's my y? Omega RL. And you guys will see the denominators will cancel. Omega square L square. So one of the omegas cancel, one of the L's cancel. And the angle becomes, the phase angle becomes tangent inverse R divided by omega L. And here the ratio of corner frequency is defined as the ratio of R divided by L. So in the previous case, omega C is R divided by L. In the previous case, it was 1 divided by RC. Okay, so this is, you don't even need to worry about that. The main idea is the important point is on the frequency response when we're plotting. So when your omega equals to omega 0, right? So in order to have that, what we're looking at is when omega equals to omega 0, so then this is going to become 1 and this is going to become 45. And the same idea is like, where does this expression has come from? You can derive this expression from here, but we're not doing that, okay? So you can derive this expression how? You know the magnitude is going to be 0.707. So put this as 0.707 and then solve for what value of omega that comes to. And then you define it as omega 0. But for our discussion, it's okay if we can just know that in this case we're assigning omega 0 equals to r divided by L. Okay, so in that case, your phase angle expression is going to be tangent inverse omega 0 over omega. And just give me a second, okay? I want to check something. And also keep in mind here we have positive, okay? Because here the J is positive, so tangent inverse y over x. So this is a positive angle, not negative as the previous case. R over L basically gives you that. I don't know if that is a problem or not. That's all right. So similarly, we can try to change that R over L in this expression as well, but I'm not going to do that, okay? And you can leave the magnitude and the angle expressions as it is, and saying omega 0 is given by R over L. Seems like okay, guys? Did not make any mistake? Say that again. The tangent inverse, like this one here, right? So that's your x. Did I not write it correct? Okay. So the main idea is, since the denominators here in y and x remains the same, so I basically skipped writing this. I simply write omega RL, and since then the x is in the denominator, so it's omega square L square. So this is the omega square, this is the L square. One of the omegas cancels with the square, one of the L's cancels with the L square as well. So it leaves R in the numerator, omega and L in the denominator. Make sense? So maybe if this is confusing, I can cross it like this. So it's omega square L square. Anything else? Okay, so let's see how does the response of this circuit looks like. So when you plot again, anyone has any questions on this page? So first we develop the transfer function, then we change the transfer function in a form that it's a complex quantity, so it should not have any J in the denominator. Then once we have it in the rectangular form, we're simply changing it to a polar form. And the only way right now, because it's all unknowns, we don't have any numbers, we cannot put the numbers into our calculator. So that's why the only way we're left with is changing manually from the rectangular form to polar form. And this is simply the polar form of that H. Right? Any questions we have? Okay, so let's move on and let's say what is this phase plot looks like and what does its magnitude plot looks like, okay? So again, on the magnitude plot, we're going to have the magnitude of H on the y-axis. We're going to have omega on the x-axis. And somewhere here, we can say is the value of omega equals to omega 0, which is given by R over L. Okay, and the graph looks like this. So this value, let's assume, is 1. And somewhere here is 0.707. So at 1, it's 0.7. Sorry, at omega 0, it's 0.707. At low values, it's 0. May not be a very good way of drawing this. Or let's change this slightly to the left. And then I'm going to move this dot as well. Okay. And for high values, looks like that. Similarly, if we're looking at a phase plot, it's the positive value of the phase angle. So it's the angle HJ omega here, and it's again the omega on the x-axis. And let's assume here, somewhere here is omega equals to omega 0, which is R divided by L given. And in this case, at omega 0, and you can see it's going to be 1, and that's going to be from tangent 45. So 45 is almost here, 45 degrees, and above that it's going to be only in the range of 0 to 90, okay? So 45 and 90, so and your value changes like this. So here what we're concluding, at very low frequencies, or at low frequencies, doesn't matter you write very or not, at low frequencies, okay? At low frequencies, when we're saying low frequencies, so we're saying omega less than omega 0. So gain is 0, or gain is small. So when I'm saying approximately equals to 0, I mean you can you can always change this. Look here, guys. You can always change this plot, like saying it always remains 0, and here it changes to 1. Like this is a theoretical graph. And the dark blue is practical graph. So here in the light blue graph, all you're saying is binary 0 and 1, right? Gain is 0 and maximum. So for low frequencies, for omega less than omega 0, the gain is approximately 0 or low, you can say, okay? So that means whatever signal you're sending in, none of it is coming out. Make sense? So you have V output equals to something times Vn. Now, right now, that something is 0. So that means V output is going to be 0 multiplied by Vn, meaning you have input signal, but there's nothing coming out. Okay? So then we're going to say at high frequencies, omega greater than omega 0. So we're saying gain equals to 1. If gain equals to 1, so your V output equals to V input. So that means whatever you're sending in, the same thing is it's giving to its output. So what type of signals this circuit will let go through it? High frequency signals. What type of signals this circuit will block? Low frequency signals. Make sense? Right? Do we understand the significance of this? Like what frequency response is? So that's what we know from these graphs, saying, okay, this passes. So I'm going to say this circuit passes high frequency signals. And blocks low frequency.